Hello there, my name is Sultan Saeed, and today I'll be talking to you about my design presentation for my HALE UAV wing. Now let's start off with my design requirements. So to start off with, the thin air at high altitude is cold due to the low pressure. Now at a height of 25 kilometers, for example, the air ambient pressure and density are around 2.45 and 3 to 3.26% of their average values at sea level respectively, while the temperatures are approximately minus 50 degrees. Now, these properties affect the vehicle's ability to generate sufficient lift forces to retain its weight. Now, as a result, while building these high altitude aircrafts, the multidisciplinary design optimization approach will be critical. In the sections following, we'll summarize some of the major problems. To start off with, we will talk about the elastic deformation. Now, the be-all and end-all is it has to be flexible. Now, HALE airplanes need to have broad wingspan and a lightweight constructions to allow them to be flexible. Now, as a result, the aerodynamic load will have a major impact on the wing shape, which will affect the aircraft's aerodynamic performance and stability. If the deflection is great enough, the aeroelastic behavior will dramatically alter, perhaps leading to non-linear aeroelastic behavior. Now we get on to the power requirements. I chose for a solid HALE UAV. Now, solid HALE UAVs operate mostly on the solar irradiance for energy, which is affected by the time of day, the time of year, the latitude, the altitude, and so on and so forth. Now for long duration flights, the aircraft should continuously fly. If energy is required, if energy is generated during the day to sufficiently power the aircraft for the whole 24 hours. Now we get on to the next section, which is material. Now, since my aircraft will be up in the sky for a long period of time, the most important design requirement is to consider how I could keep it in the air for the longest amount of time. Why that? With the aircraft being lightweight, there's less bearing on the aircraft for me to allow an increase in the storage of things like fuel or fuel cells when it comes to my solid HALE UAV. So let's talk about the preliminary constraint performance values. Now, if we look at the first one, we have a value of cruise speed. Now, cruise speed is the speed at which the HALE UAV will be traveling at whilst performing its missions of surveillance and other military activities. Now, the second one I calculated was the cruise altitude. The cruise altitude is very, very important. The cruise altitude tends to be chosen between 15 and 30 kilometers for several reasons. First of all, it takes place well above the civil aviation airspace, leading to an easy operation of the UAV, as well as presumably an easy certification. Now, a high cruising altitude furthermore leads to wider area coverage, which is much easier for when the military are conducting their missions. Now, given the factors I had to use to calculate my wing height, there was another reason for adopting this chosen cruise altitude. As you can see in figure 1, a low wind speed can be seen between 15 to 25 kilometers at altitude, not too far off my calculated altitude. Now, sustained flight at high altitudes involves a range of difficulties. The thin air at high altitudes is cold at low pressures, as mentioned before. And finally, my last calculated performance constraint value was my weight, which amongst other average UAVs tended to fit well as well. Now, leading on to from our previous preliminary constraint values, I was able to then calculate the following values. First one being the Mach speed, which came out to be 0.088. Then leading on from that, I was able to calculate the dynamic viscosity, which I needed to use to calculate my Reynolds number. Now, for my dynamic viscosity, I came up with a value of 1.4698 times 10 to the minus 5. With that led on to my Reynolds number, ending up being 8,363.74. Now, I was then able to research my aspect ratio, as the aspect ratio I came up with looked to be a little bit off and didn't seem to fit with my wing design requirements. Now, as you can see from figure 2, with the examples on the graph, a steeper gradient suggests that with a slight angle of attack pitch, the lift coefficient would increase dramatically. Now, with my aspect ratio being 23, you can imply that with such little movement, the coefficient of lift would be significantly high. Now, when it came to my aerofoil design, I had to research around for an aerofoil similar to the one I wanted to use. Now, the best aerofoil design I found was with the NASA RQ-4 Global Hawk UAV. The aerofoil name came out to be LRN 1015. Now, as you can see with this distinctive shape, it's got a slope at the back of the wing. The Reynolds number that I did calculate with this wing came up to be 100,000. This was a very suitable Reynolds number, as the one I calculated before was too low for it to even compute a design analysis, which you will see further on in the slides. My maximum coefficient of lift ratio, so coefficient of lift and drag ratio, came out to be 39.77, where the angle of attack was 9.75. With the description, a rough L calculation of my Mach number came out to be 0, rounded down. Now, with my aerofoil LRN 1015 wing design put into XFLR5, I was then able to compute these graphs which would show me my design analysis. Now, if we take a look at the second graph at the top, you can see that as the angle of attack increases, so does the coefficient of lift, up until it hits its maximum angle of attack of around 15 degrees. At this point, the angle of the lift coefficient stops to conform as it was doing so before and starts to decrease. Now, this can be suggested that 15 degrees, roughly 15 degrees, would be the stall angle. Now, this would further be reinforced by the graph at the bottom right corner, where as the angle of attack increases, so does the lift ratio, up until it hits to a point of around 10 to 15 degrees, where at this point everything reverses and the coefficient of lift starts to plateau, which would imply that drag is the major force taking place. Now, this is an add-on from the single design analysis, where I took a variety of angle of attacks and put that against a sequential iteration for it to produce the following graphs. Finally, with all things considered, as well as the aerofoil of my Global Hawk, I was then left with my final wing design. Thank you very much for taking the time to listen to my design presentation. Thank you.